So we're going to start reviewing for our exponential family. Now tomorrow you're taking this English STAR test, but we're going to have class on Monday and Wednesday and Friday. And Thursday you're going to be taking your practice algebra STAR test. So you may see some of these on the practice test. We thought we'd at least get a little bit into that before we have the practice test. The parent function is y equals b to the x. Now how do you know that these are called exponential? Now remember, an exponent is that small number raised up high. Look over here. When we had linear equations, it was y equals x, and x was to the first power. In quadratics, it was y equals x squared, and x was to the second power. This time, the x is the exponent itself. X is the little thing raised up high. In the other two, linears and quadratics, the x's were the bases. So they're different. Exponentials have the x as the exponent. This is what the formula looks like, or the basic equation is y equals ab to the x. What we're going to do is just pick out what the parts are. This first number up here that's not being raised to the x, the one that's by itself, these are being multiplied together. This first number without the x is the starting amount. It's your y-intercept. How much did you have at time 0? The b is the growth or decay factor, because these are either going to be growing or they're going to be decaying. And x is the time period. Okay, now I know it's going to sound crazy right now, but once you start doing these, they're really, really easy. What shape do these make? They don't make a straight line. They don't make a parabola. If it's growing or increasing from left to right, we always read left to right, it is going up. Okay, never comes back down like a parabola, it just keeps going up. Decays, on the other hand, are decreasing from left to right. It's coming down, and then it flattens out. Let me make that better. It comes down and flattens out, and it keeps flattening out and just keeps going and going that way. Okay, now they call this line down here, and most of the time the horizontal asymptote is going to be this x-axis. What that means is this graph never touches or crosses this line. It never crosses or touches the x-axis, which means there are no x-intercepts, there are no solutions. What's the equation of this horizontal asymptote? It's a horizontal line, hoi, so it starts with y equals, and what is the y number that that line is crossing at? It's crossing at 0. So that x-axis, the equation of the x-axis is y equals 0. They call it a horizontal asymptote because the graph approaches it but never ever touches it. It gets closer and closer and closer the further out it goes, but it never ever touches or crosses it. So that's what that is. Now, what kind of situations do this? They are things that grow exponentially or decrease exponentially. Populations, cells growing into a baby. You have one cell, it splits into 2. Those 2 cells splits into 4. 4 cells split into 8. 8 into 16, 16 into 32. They increase exponentially. The pandemic that we have, or in the middle of still, it started off with one person sick, and then 2 people are sick, and then they infect, each of those infect 3 more, and each of those infect 3 more, and before you know it, the whole population is infected, or at least a big chunk of it. So those are when that's growing up is expanding faster and faster. It starts off slow, just at 1 person, and then 2 people, then 4 people, then 8 people, and then all of a sudden it starts exploding up and just goes up exponentially, hence the term exponential. Okay, and same thing coming down. Once they get a cure or they get some drugs or they get something to treat it, it starts coming down. So you can look at bacteria growing in a petri dish. It will start taking off exponentially. You put in some antibiotics and all of a sudden it starts decreasing exponentially. Same thing, populations in the wild. Crickets and things will have a great food supply and no predators, and all of a sudden their population takes off and grows exponentially, and then all of a sudden a bunch of birds move in, migrate in, and now all the crickets get eaten up, right? So things can increase and things can decrease. So there's lots of things that will do that. Radioactive material, you heard radioactive decay. That's the shape of this would be when the material is decaying. So you've got radioactive material, and over time it decays and becomes less and less. It comes down really fast and then it flattens out, and so it lingers for a long, long time. So anyway, that's what we're doing this week. All right, let's go look at this worksheet. Now, it may look like this is a whole lot on this worksheet, but trust me, it is not really, because these go really fast. When you're looking at this, you read the graph from left to right. So we just want to know whether it's growing or decaying. Remember, growth is increasing, decaying is decreasing. So from left to right, are you going up or down? We're going down, so this is decay. The big thing is just being able to label it decay, because in a word problem, if they talk about something decreasing, you know it should be looking like this. If they talk about something growing or increasing, it should look like this. Okay, so these are exponential growth, exponential decay. So you got to be able to pick out what they are. Tell whether the following equations represent exponential growth or decay. This is really easy to do. And again, this is the poster that you have. This b here, the base number of your x, which is the exponent, it is your growth factor or decay factor. If this number is bigger than 1, if it's 1.2, 1.8, 2, 2.3, 3, anything bigger than 1 means the graph is going to go up. It's a growth situation. If this number is less than 1, 0.9, 0.8, 0.2, 1/4, 1/2, anything like that, it's going to be a decay situation. So all we do is look at this growth or decay factor. If it's bigger than 1, it's growing. If it's less than 1, it's decaying. This is your initial amount. What was the population at time 0 before it started taking off? How many crickets did you have before the population started exploding? Once the birds moved in, how many crickets did you have before it started decaying because the birds started eating them all up? So let's go look at these and see. They want to know if it's growth or decay. So all we do, this is the initial amount, but this thing that's being raised to the x is my growth or decay factor. Is this one growing or decaying? Well, is 3/2 bigger than 1 or less than 1? If you're not sure looking at the fraction, put it in the calculator. So on the add subtract screen, if you put 3/2 and do Control Enter, it will tell you it's 1.5. Is 1.5 bigger than 1? Yes, it's a growth. So you need to be able to look at an equation. You know it's exponential because the x is the exponent. Over here, it's exponential because x is the exponent. Here's my growth or decay factor. Is it bigger than 1? Yes, so this is growth. We're just picking out if it's growing or decaying. Y equals 2 to the x. Now, you may say, well, there's only one number here, but yes, it's the one with the x, so that is your growth or decay factor. Is it bigger than 1? Yes, this is a situation that's actually doubling. So this is a growth. Now, you might say, well, what happened to the other number? It's there. It's just 1 times 2, right, to the x? So the initial amount was 1. You had 1 something before it started growing. Okay, again, this is the initial amount, but this is your growth or decay factor. Is it bigger than 1 or smaller than 1? Smaller than 1, so that's a decay. It is going down or decreasing. This one, this is the number being raised to the x. Is 0.5 bigger or smaller than 1? It is smaller, so this is decay. It's coming down, it's decreasing. What was the number in front of that? You would have a 1 times that 0.5 raised to the x power, right? So you start off with 1 something. Okay, next section. Give some examples of exponential growth. This could be populations growing. So populations tend to grow exponentially. Let's see, baby cells, growth of cells. You could, how would you say it? A child, any animal growing from a single cell, right? Animal growing from a cell. You can put that. Because you start off with 1 cell and then they split and split and split. Other things that grow exponentially, population, sizes, weights, things tend to, animals that growing. There's a whole variety of them when we start doing the worksheets and stuff. Things that tend to decay, well, radioactive material decays. Radioactive material. Populations. Populations can grow and populations can decay. Latins. There's a whole bunch once we start seeing some of the problems and stuff in here. You'll see tons of them. Diseases, and we can have diseases both ways, right? We should put diseases. I can't believe I forgot about that one over here. So diseases can grow when they first start taking off, and then diseases can decay once we get cures and stuff for them, right? Because there's hardly any polio anymore after they got the polio vaccine. Okay, so let's look at the next page. And there's all sorts of variety of things that grow exponentially and decay exponentially. So here they want to know, all exponential functions are in the form y equals ab to the x. Y is your total amount of any given point. X is your time period. So is it 1 week, 2 weeks, 3 weeks? You can plug in whatever number you want to find out what the population is at 2 weeks or what the population is at 5 weeks. So whatever the population is at whatever weeks or months or whatever days, whatever the time period is that they're doing. Could be yearly, could be monthly, could be weekly. A is your initial amount, and B is the growth or decay factor. So what values of B make it exponential growth? Bigger than 1 or less than 1? Yes. If B is bigger than 1, it's going to grow. What values of B make it decay? Anytime B is less than 1. Okay? Label each function as either exponential growth or exponential decay. So is this one growing or decaying? You're right, this is a decay. It's coming down. Always read left to right. Left to right, is it going up? So that's a growth. See, I told you this was an easy day. Left to right, coming down, so that's decay. And yes, it is also decreasing, but they use the words in exponential growth and exponential decay. Label each function either exponential growth or decay. This time they're not giving us a picture, they give us the equation. This is the initial amount, but this is my growth factor. Is it bigger than 1? Yes, so it's growing. Here's the equation, here's the initial amount, and I've got 7 crickets before the population does something. Is it bigger than 1? No, it's less than 1. So this one is decaying. Some of my 7 crickets are about to kick the bucket. Here's again what we started with, 1.9 something. It could be 1.9 million somethings, it could be 1.9 thousand somethings, we don't know. This is my growth factor. If you're not sure if this is more than 1 or less than 1, put 5 halves in the add subtract screen in your calculator, hit enter or control enter, and it will tell you it's 2.5. So is that bigger than 1? Yes, this is a growth situation. Whatever we're talking about is growing, increasing. All right, here's another lovely one. So again, the plus and minus is on the end. Don't worry about those. It's just we're focused on this piece in here. So y equals some number being raised to the x power. So this is my initial amount, this is my growth factor, and x is my time period. So is it bigger than 1? Yes, so this is growing. We just want to get comfortable with these parts. Initial amount is the number in front. The 2/7 that's being raised to the x, it's whatever's being raised to the x is your growth factor. 2/7 is less than 1. If you're not sure, put 2/7 in the calculator and look at the decimal answer. And this is a decay. Decay. Again, initial amount, you have 250 somethings. This is the growth factor. It's being raised to the x power. Don't worry about the numbers on the end like that. We're not concerned about those this year. But this is decay because 1/9 is less than 1. So this is a decreasing graph, not a growing graph. All right, given the equation, so here's my lovely equation. Does this equation represent growth or decay? So you can do it over here. I'm just going to keep it here where I can see it and just circle it. Is 0.57 bigger than 1 or less than 1? Less than 1 is decaying. What is the growth or decay factor? It is 0.57. That number that's being raised to the x is it. Now, this is asking for the actual rate, and we're going to talk about that another day, so do not worry about this question. We're not going to do C on any of these today. We'll talk about that tomorrow or Wednesday whenever we do this again, or maybe Friday. What is the initial value? It's 35 somethings. I don't know what we're doing or talking about here, but 35 is the initial amount that we have. At time 0, my y-intercept is 35. The starting amount is my y-intercept. Remember that? Same thing on linear, same thing on quadratics. The y-intercept is your starting amount. I got 35 somethings to start with. So here we go. Here's the equation. Is it growth or decay? Well, if you're not sure, you think there should be two numbers. This is 1.3 being raised to the x, and what number is sitting in front of this? There's being a 1 multiplied times it. Now, you don't have to put them both in parentheses if you don't want to, but there's a 1 sitting there, okay? So it's 1, something to start with, times 1.3 is the growth factor, and this is raised to the x. So whatever is raised to the x is the growth factor. Now, or decay factor. Is it bigger than 1? So it is a growth factor. Had it been smaller than 1, it would be the decay factor. What is the growth or decay factor? It is that number 1.3. That is the actual factor. We're not going to do the rate. We'll talk about another day how to find that. What is the initial value? We started with 1 something, right? You don't see it over here, but when you do it like this, you can see there's 1 something that we started with. New equation, it's exponential because x is the exponent. Oh, by the way, if you want to put these in the calculator, you know how to do start, the graph icon. You got your y equals, and you can type in 1.4, parentheses 1.03, close it. Now, to put x as the exponent, you have to do that little rooftop key. That raises it, and then you can type in x, and that will put the x in as the exponent. So you're going to use that little rooftop key to raise it to the x power, and then type in x. Okay, so here it is. We want to know if it's growth or decay. Is this number bigger than 1? Yes, so it is growth. What is the actual growth factor? It is 1.03. It's not much bigger than 1, but it's bigger than 1. What is the rate? We're not doing that part. What is the initial value? Which of these is the initial value? That right there, that's my y-intercept, my starting amount, 1.4. It might be actually 1.4 cells, or it could be 1.4 million cells. We don't know. Given the equation, we want to know, is it growing or decaying? Is 0.75 smaller than 1 or bigger than 1? Because don't look at this number. We look at the one that has the x as the exponent. This is the growth or decay factor. It is decaying. What is the growth or decay factor? It is that 0.75. That is the factor. We don't care about the rate right now. We'll do that another day. What is the initial value? We have 16 somethings to start with. Here's a new equation. It is exponential because x is the exponent. Is it growing or decaying? 0.95 is less than 1, so it is decaying. It's decreasing. What is the growth or decay factor? It is the 0.95. We don't care about the rate today. What is the initial value? 4.5 somethings is what I started with. Maybe 4.5 cells, 4.5 pounds of radioactive material. I don't know what it is, but it's something like that. Okay, let's see what else we have here. Flip this over. We get one more for this. So they want to know, or each of these, are they quadratic, linear, or exponential? And then they want to know, is it an increasing function, a decreasing function, or in the case of parabolas, positive or negative? So let's look at this one. Obviously, it is quadratic because it's a parabola. So quadratic. So when they ask whether it's quadratic, positive or negative quadratic, remember my smiley face and frowny face? Was the a positive number or a negative number? It's a frowny face, so it's a negative quadratic. All right. Here is a, what shape is this? It's not linear, it's not quadratic. This is my exponential. Is it growing or decaying? From left to right, it's going up, so this is exponential growth. All right, I guess I should have put the answers up here at the top. This one obviously is linear, right? I'm going to put it up here where it's supposed to go. Is it a increasing linear? They use increasing or decreasing. It could also have been positive or negative, for the slope. Is it going up from left to right? Yes, so that's positive or increasing. You can say it either way, linear positive or linear increasing. Down here, it's not a parabola. It is not, you don't see it coming up the other way. It's just, they're showing it here and keeping going that way. So this is exponential, it's not linear. So I'm going to put it up here, exponential. I'm going to abbreviate that, exponential. And it is coming down from left to right, so it is decay. Exponential decay. Another linear. Is it increasing or decreasing? It is increasing, so that would be a positive or increasing because the slope is going up. 6, parabola again, so this is quadratic. I'll abbreviate that, quadratic. Is it a smiley face or a frowny face? It's a smiley face. So was it a positive A? Yes. It was a positive quadratic. There we go. Now, they have a couple of tables down here. I'm not going to get into too much detail on this, other than we just want to kind of decide if the pattern is making a linear or quadratic or exponential. So if they're adding and subtracting the same number over and over and over to get the next number, they're linear. If you're multiplying to get to the next number over and over and over, then it's exponential. Okay, and parabolas change direction. So first of all, look to see are the numbers going down or up or changing direction. 100 to 10 is down, 10 to 1 is down to 1/10, down to 100. These are all getting smaller. So are we subtracting the same thing? Let's see if it's linear. 100 to 10, I subtract 90. And that is not going to give me, well, that's 90 if I subtract 90, but if I subtract 90 from 10, I don't get 1. So it's not subtraction. So this was something that we're multiplying. We're actually multiplying by 1/10. 1/10 of 100 is 10. 1/10 of 10 is 1. 1/10 of 1 is 1/10. So we're multiplying by 1/10, which means this is exponential. And since it's decreasing, it will be exponential decay. And I'm not really too concerned with these. I'm actually going to take these off the worksheet today. I don't want to really look too much at them. This one, 1, 4, 7, 10, 13. Are we adding 3 each time? So this is linear, and it's increasing, so that's a linear. 1/3 to 1 to 1 to 3. Are they increasing? Yeah, they're getting bigger. Are we adding the same thing? This is plus 2, but 2 plus 3 is not 9. So we're not adding the same thing. We're actually multiplying times 3 each time. So if you're multiplying times 3, that is a exponential, and that means it's growing. Now, since we're multiplying by 3, remember our sequences, arithmetic and geometric. So this is, linears are also a arithmetic sequence because you add and subtract. Exponentials are also geometric because you're multiplying the same number over and over. So just a little tidbit to in there. And this one, 22 to 17, you're going down, 17 to 12, all going down, going down. None of these were parabolas, they didn't change direction. But we're subtracting 5 each time, it looks like. So that is also linear. So if you're adding and subtracting, those are linears. If you're multiplying to get to the same number, this is times 1/10. Times 1/10. Times 1/10. So each time I'm multiplying times 1/10. So if you're multiplying to get to the next number, they're exponential, and exponentials are also geometric sequences. Adding and subtracting to get to the next number are linear, and they will also give you arithmetic sequence. That's it. Next worksheet will be a review.